So now we will discuss how to measure the power MOSFET characteristics on the kit. So what we are seeing here is the kit available in lab for VI characteristics of MOSFET. So in this experiment we are supposed to perform the following three tasks as follows. First is to measure VGT, that is a gate threshold voltage. Second is to find the value of transconductance GM, and third is to plot the VI characteristics of power MOSFET, that is a plot of IDS versus VDS for different constant values of VGS, VGS1, VGS2, VGS3. So now we will paste the kit again to show how to connect the different meters. But we can connect the meters here only. So in order to measure VGT, that is the value of gate to source voltage at which the MOSFET starts conducting a current of minimum 250 microamperes. So we'll put the meters. So there will be one meter here which will measure the VGS for us. VGS plus and minus. So here we have our variable DC power supply. Similarly, we have another DC power supply here. This is variable. So ideally this is called as VDD. We have 1 meter connected here, which is a DC ammeter, which will measure IDS. So 1 voltmeter, 1 DC voltmeter to measure VGS, 1 current meter to measure IDS here. And in order to have accurate readings, we can connect one more meter here, which will measure VDD for now. Okay, and this is our VDS voltage, and since there is no socket which is provided to connect to the drain terminal, in this kit we cannot measure the VDS by connecting a voltmeter between drain and source terminals. Only if this socket would have been here, then by connecting a voltmeter between this socket and this socket we could have measured VDS directly, but that is not possible here. That is why what we do is that we consider the equation VDS is equal to VDD minus IDRD, and the value of ID is known to be approximately equal to 1 kilo ohm. So the value of this voltmeter VDD minus the value of this current meter IDS into 1000 ohms will be the value of VDS. So now we'll show the kit again, and we will also tell the conditions to be applied in this kit to measure VGT. Okay. To measure VGT. So students, understand, VGT is that value of VGS for which the drain current is equal to 250 microamperes for VDD equal to 10 volts, right? So VGT is that value of VGS at which the drain current is equal to 250 microamperes for VDD equal to 10 volts. So we have to impose these conditions on this circuit here. Okay, so here is our VGS meter, and here is my VDD meter, and here I have to keep it as 10 volts, and here is my IDS meter. Okay, and the steps are: first, keep VGS equal to 0 volts. So students, this is to be kept as 0 volts. Okay, 0 volts. Second thing is, keep VDD equal to 10 volts. So we already kept VDD as 10 volts, already kept VGS as 0 volts. Okay, so what we will note, when VGS is equal to 0, and the value of VGT is anything which is greater than 0, which we do not know. So for VGS equal to 0, the channel is not formed. So we will observe that the IDS meter shows a value 0 amperes. So now increase VGS above 0 volts. Now students, what you have to do is, from delta VGS equal to 1 volts for the range 0 volts to 3 volts, and once VGS is equal to 3 volts, beyond that the value of the change in VGS is equal to 0.1 volts for greater than 3.4, greater than 3 volts. Okay, so fifth step is that increase VGS and note every new value of IDS, and increase VGS till IDS is equal to 250 microamperes. Okay, so when IDS is equal to 250 microamperes, note the value of VGS as VGT. So our first bit is found here. Okay, so when IDS reaches 250 microamperes, this particular value at which this happens is called as VGT. Okay students, so now the OBS table for this bit becomes something like this: VGS in volts and IDS in milliamperes. So as we have told that you have to increase VGS in steps of 1 volts from 0 to 3 volts. So 0, 1, 2 and 3, and beyond 3 it is 0.1 volts. Okay, 3.6, say up to 4.0, and every new value of VGS you have to note. Okay, so for example, at 3.5 volts you get the current as 0.25 milliamperes or 250 microamperes. Then students, please note that this is nothing but your VGT. So note VGT as 3.5 volts here. Okay, so students, this is nothing but a observation table which can be used to plot the transconductance characteristics, that is IDS versus VGS. So here we can see This can be your IDS in milliamperes, and this is your VGS in volts. So it is 0, 1, 2, 3, and 4. And somewhere here at 3.5 you get it, right? So this is our 0.25 milliamperes. So this will happen here somewhere. So the graph will go something like this. Almost becomes constant. Okay. So if this point and this point, so yes. So my transconductance Gm be equal to delta IDS upon delta VGS. Okay, so first two bits are already done here. Now I go to the third bit, that is plot the IV characteristics of our MOSFET. So again, so plotting IV characteristics is nothing but plotting the output characteristics. So it is IDS versus VDS for different constant values of VGS. Okay, so what are the steps involved here? The meters remain the same. IDS VDD plus and minus. Okay, and this is my VDS, right? So step number 1, for VGS equal to VGS1, the first step is set VGS equal to VGS1, which is equal to gate threshold voltage plus 0.02 volts, which in our case will be 3.52 volts. Second is set VDD equal to 0 volts. Third, increase VDD in steps of 10 volts, 5 volts in fact. Note the new value of IDS for every new value of VDD. Fifth is that calculate VDS as VDD minus IDS into RD, where RD is equal to 1 kilo ohms. Okay, the last steps are sixth. Repeat steps 2 to 5 for VGS2 and VGS3, where VGS2 is equal to VGT plus 0.04 volts, which in our case will be 3.54 volts, and VGS3 is VGT plus 0.06 volts equal to 3.56 volts, and tabulate your readings as per the OBS table. Okay, thank you.